Hi everyone, my name is Sanjay and welcome to my YouTube channel. So in this NLP series, currently we are discussing deep learning for NLP. And in deep learning for NLP, in the last video, we discussed about encoder-decoder model. And in this video, we'll discuss about attention mechanism in encoder-decoder model. So this is an improvement upon the previous video or previous topic, that is the encoder-decoder model. There we'll introduce one more concept called attention mechanism. So this attention mechanism will help the encoder and decoder model in processing text in a better way. So this will improve the performance of the encoder decoder model. And this attention mechanism is based on a paper from 2014, and that paper was created for machine translation. And don't confuse this attention mechanism with the self-attention. The self-attention was mentioned in paper from 2017. The paper name was Attention is All You Need. So it came out in 2017 from Google. And the transformer block mentioned in that paper is the basic building block of current LLMs. So all the LLMs, all the ChatGPT, Gemini, whatever you see currently in the NLP field, all are based on the transformer block mentioned in the self-attention or the attention is all you need paper from 2017, which we'll discuss in the next video. But currently, we'll just discuss the attention mechanism. It will help in understanding the self-attention as well. So that's why I wanted to discuss. So you just need to understand why we need it and how it's working. So this will help in understanding the self-attention. So you don't need to go deep here. You don't need to understand all the mathematics on the attention mechanism. Just understanding high level is good enough. So let's dive deep into this. So before diving into the attention mechanism, let's first understand the problems with the simple encoder-decoder model. And this will help us in understanding why we need the attention mechanism and how it's helpful. We have seen this encoder-decoder model in the last video. First component here is the encoder, and then we have decoder, and in between we have the context vector. So the context vector is the output for the encoder model, and it also input to the decoder model. The context vector is a kind of summary of the whole input. So the whole input sequence is, you can say, summarized or encoded into this context vector. Okay, so this is what encoder and decoder model is, and we have discussed this in the last video as well. So let's look into the problem first. The first problem is lengthy sentences. As the length of the sentences increases, the performance or the accuracy of the encoder-decoder model is going to decrease. And the second issue is not human-like. So for this to understand, let's look into an example. Consider a machine translation task. So suppose we are doing a machine translation and we have input in English. So this is our input, which is in English, and this is our output. So we are translating from English to Hindi. Basically, we are translating from English to Roman Hindi. This is Roman Hindi because we are using English alphabet in this Hindi sentence. Okay. So this is our translation task, machine translation task. And when we generate the token, generate the word in the output. So as a human, when we generate the first word for the machine translation, instead of looking into the whole sentence, we'll look into phrases from the sentence. So for generating this sentence, sorry, sending this word, bache, we'll first look into this first two words. Okay, so first two words from this English sentence. The children. So next, to generate the next word, this is the next word in the output, bagiche, right? So this is the word. And to generate this word, next word, we'll look into the other section, other phrases in this sentence. So we will look into this, the garden. So our focus will be the garden while generating the second token, and so on. So here, as a human, we focus on parts of the sentences or phrases from the sentences, while generating the tokens in the output while doing this machine translation. And this same thing applies for summarization and question answering as well. But when we mention in the encoder-decoder model, what we are doing, we are passing the whole sentence, basically, right? In the context vector, we are passing the whole sentence. Instead, we should pass phrases of sentence, or we should focus on the phrases of sentence. So that's what the encoder-decoder model does. So it solves these two problems. One is the length, and next one is the focusing on particular parts of the sentence while generating the token. So we'll see how the how the attention mechanism works. So let's look into an example of encoder-decoder model with attention mechanism. So this is a diagram of an encoder-decoder model with attention mechanism. This part is our encoder model. This is you have seen this diagram because this is a bidirectional RNN. So in the encoder, we'll use BRNN. We have discussed BRNN in one of the previous videos. So I would recommend you to watch that video. So this is our BRNN, which is our encoder model or encoder component. And here we have this decoder component. Okay. In between, we have the attention mechanism. So this is the attention mechanism. This is the magic. This is where the magic happens. We have this input x1, x2, x3, x4, and for each of the input token, we'll have a hidden state. So for x1, we have hidden state h1, x2, we have hidden state h2, and so on. And for each of the y1, we'll have c1, c2, c3, 4, c4. So for each of them, we'll have a c. Basically, c1 is for y1, c2 is for y2, and so on. And this C1, C2, and so on are context vector. So unlike in the traditional or simple encoder-decoder model, where we have a static and context vector, right? Where we had a static context vector, we saw in the last video as well. In this attention-based encoder-decoder model, we'll have a dynamic context vector. Basically, for each of the output token, we'll have a separate context vector. So here we are seeing a different context vector for different output tokens. And you'll see how it's calculated, how it's computed. Okay, so let's focus into this attention mechanism in the middle part. Then we'll look into the decoder part. So in the attention mechanism, we have this hidden state, which are output from the encoder, and we have this C1, C2, C3, C4, which are the context vector. And we use the hidden state to calculate the context vector. Basically, this is the formula. C1 C1 or Ci equals to summation of alpha ij hj. So this is the hidden state. This is called attention weight. So this is the attention weight, and the summation range from j equals to 1 to tx. So that means tx means number of input tokens. So here number of input tokens is 4. So this summation will range from 1 to 4, and we'll do a multiplication of alpha ij and hj. Okay, alpha is the attention weight. Basically, how much weight we are giving to each of the hidden state. That's the idea with attention mechanism or the attention weight. For calculating this C1, we'll have to multiply H1 alpha 11, H2 alpha 12, H3 alpha 13, and H4 alpha 14. But we have not shown the alpha 13 and alpha 14 because the weight for the alpha 13 and alpha 14 is 0. Okay, we are saying that weight for alpha 13 and alpha 14 is 0 because our focus here is H1 and H2. So for outputting the first token Y1, we'll focus on the first two tokens and we'll ignore the rest. So that's why the weight is 0 for these connections. That's why we have not shown them. So basically, a C1 formula for C1 will be H alpha 11 H1 plus alpha 12 H2. Okay, this is our formula for C1, and the other terms will be 0. And this H1 and H2 are output from the encoder, and the alpha 11 and alpha 12 are the attention weight, basically giving importance to. This is basically a way to give importance to the hidden state. So how much importance will be given to H1 and how much importance will be given to H2. Here you see this is slightly bolder, this arrow, than this. So that means we are giving more importance to H1 than H2. That means the alpha 1 is bigger than alpha 12. And for calculating the C2, that is the context vector for the Y2, we are having three connections from H1, H2, and H3. That is alpha 21, alpha 22, and alpha 23. Okay. Uh, Here you see the importance is higher for alpha 22, this connection. So for calculating C2, we are ignoring the H4. Basically, we'll ignore the H4. That means the alpha 24 connection is 0. And the formula for C2 will be C2 equals to alpha 21 into H1, alpha 22 into H2, alpha 23 into H3. So we'll sum all these three terms to get C2. This means that for Y2, we are focusing on H1, H2, H3, and we are ignoring H4. So we'll ignore H4 and we'll only focus on these first three tokens. So here in this attention-based encoder-decoder model, we are focusing on particular set of tokens, particular set of input tokens to produce an output. We are not focusing on all the tokens. We are not focusing on the whole sequence. We are focusing or giving attention to few of the tokens while generating one output in the decoder part. And there also we are giving importance to the tokens which are more likely to be related to the output. And that's what the attention mechanism is, giving importance to few tokens while generating the output and ignoring the rest. So now we have seen how to calculate the context vector. We'll see how we use context vector in the decoder part. Basically, in the first time step, we'll output y1, and we have seen that first input to the decoder model is the start token. Okay, so this is the start token, and now along with the start token, we'll have this context vector c1 in the unit, and we will also have a hidden state S0. So S0 is the hidden state. So all these three will be input to this unit, and this unit will produce output Y1. Okay. So in the next time step, this Y1 will be input to the next time step, as we have seen in the encoder-decoder model in the previous video as well. And along with this Y1, we'll have C2 calculated again for this time step, and we'll have the output from the previous unit. Is S1 is the output from the previous unit. This is a hidden state basically, not the output. This is the hidden state from the previous unit. So you'll use this hidden state S1. We'll use the C2. We'll use Y1 to produce Y2, and so on. So this is how the decoder works in the attention-based encoder-decoder model. This attention-based encoder-decoder model or mechanism was mentioned in this paper, Neural Machine Translation by Jointly Learning to Align and Translate by Bahdanau et al. In 2014. The attention mechanism is shown in a simpler format, but you'll see this is slightly complex than this. We'll see how the alpha 1, alpha ij are calculated. There is, if you see the formula for alpha ij, it will become slightly more clearer that this calculation is slightly complex than the diagram shown here. But the idea is same. So we'll see the formula for alpha ij as well. So let's first look into the context vector formula. So the formula for context vector is Ci equals to summation over j equals to 1 to tx over alpha ij into hj, where hj is the hidden state for xj, Alpha is J is the attention weight for Y1, sorry, YI and XJ. Okay. So this is the output, this is the input, and for that output and input, this is the attention weight. Okay. And Tx is the length of the input, and Ci is the context vector for the ith output. There are some constraints. First constraint is summation of alpha ij from j equals to 1 to tx is equals to 1. Basically, this is the kind of normalized where summation is going to be equals to 1 and alpha ij is greater than equals to 0. It's not going to be negative. So that means it's kind of probability. Let's look into the calculation of attention weight and alignment score. We've seen how alpha ij, that is the attention weight, is used in the formula earlier, and how it's calculated we can see here. It's exponential of eij divided by sum of exponential of eik, where k is ranging from 1 to tx. So tx means the length of the input sequence, the number of tokens in the input sequence. Eij is the alignment score. Okay, let's see how it's calculated. So this is the formula for alignment score. Alignment score EIJ is function. Here is a this is not a function. This is a feed-forward neural network basically. So this is a alignment model. This is A is the alignment model, and it's a feed-forward neural network where we have to provide the Si minus one. That is the hidden state, previous hidden state in the output sequence, and Hj is the hidden state from the encoder part. So this is the hidden state from the decoder part. This is the hidden state from the encoder part. This is the current hidden state, and this is the hidden state from the previous time step. So we'll provide this into this alignment model to get alignment score. This is also called energy, and this is used to calculate the attention weight. And to calculate this energy or the alignment score, we create this model called alignment model. And this is a simple feed-forward neural network model. Simple and small feed-forward neural network model. Now that we have seen the attention mechanism, let's visualize the attention. So basically the attention weights. Okay. So in the example, we have seen the machine translation. The input was the children are playing in the garden because the weather is nice. And our translated output was बच्चे बगीचे में खेल रहे हैं क्योंकि मौसम अच्छा है. So this is the input and this is the output. And these are the weights. Basically, they are the attention weights 0 to 1. Okay, so the attention weight can vary from 0 to 1 because the sum was equals to 1 and it should be greater than equals to 0. So we have color coded this 0 are colored as black and 1 are colored as yellow. So look into the first row. This is the first row. So let's look into this first row. This is the attention for the first token. So when we are generating the first token, these are the attentions. Okay. You see the attention for this connection for this input is 0.8, and attention for this token in the input is 0.1, and so on. And for most of them, it's 0. That means while generating this token in the output, we are focusing on these four tokens in the input. And in these four tokens, we are giving more importance to the second token here. So the second token is children, and the output here is bache. That's means children only in Hindi. And you see a similar thing in the other rows as well. For this row, the second row, bagiche, that means garden. Basically, these are the attention weight for this output token. And here you see we are focusing on all of these input tokens while generating this output token. and most important is given to this token. Okay, this token is corresponding to garden. That's the output here. Bagiche, that means garden only. And similar thing you will see for other outputs as well. Here you see for this example, Kyunki, right? Here for generating this, we are giving importance to this token only. Here attention weight is 1, all are 0. So sum is going to be 1 only. So all are 0, this is 1. And this meaning of Kyunki is because. Okay, so that's how the attention are given. And for each of the row, if you sum them up, for each of them, you'll see that the summation for each row is equals to 1. Because in the formula for Cij, we saw that the constraint was that sum of alpha 1j or sum of alpha 2j is going to be 1. So sum is going to be 1 for each of the row. Okay, and each of the alpha ij is going to be vary between 0 and 1. This kind of like probability. So this is how the attention work in the attention-based encoder-decoder models. Thanks for watching. If you have any queries, please comment. Basically, you don't need to go deep into the attention mechanism or the formulas related to this. You just need to understand how the attention mechanism works and why it works and why it's used. You'll focus more into the attention in the next video. There we'll discuss transformer, which is from another paper called "The Attention is All You Need." And there we'll discuss more into attention and there we'll dive deep because that's more important paper than this one. So just to get a rough idea of attention from this video, in the next video we'll go deep. Thanks again. See you. Bye.